In this video, we're going to be doing a rotations FRQ on a person holding a bike wheel while they are on a platform. So a person with a mass m and a radius r, they can be approximated as a solid cylinder with a moment of inertia 1/2 mass times radius squared. And they're standing at rest on a frictionless platform holding a hoop-shaped bicycle wheel with a mass divided by 10 and a radius 2r, which is spinning frictionlessly at a rate of positive omega initial. So what is the person's angular velocity after they flip the wheel over so that the wheel is spinning clockwise? Well, we know we have no external torque because this is going to be a frictionless system, which includes the rotating platform, person, body, and the wheel. So we set L initial equal to LF. Now we know that for our initial angular momentum, the person is not rotating, so they're going to contribute 0, and we know the wheel is spinning. So for the moment of inertia of the wheel, this is going to be as if you had your mass always at one distance from your center of mass, aka here is our pivot point. So we can make our moment of inertia mr squared, and we know that this is a hoop, right? But here we know that our mass is just 1/10 of it and our radius is twice. So we can plug those in. We have m over 10 times 2 times r squared. So that's going to be m over 10 times 4r squared, where we get 4 over 10 mr squared, which equals 2 over 5 mr squared. Now, in order to find our initial angular momentum, we'll just set I wheel equal to omega initial, and that will just be 2 over 5 mr squared times omega initial. So this is our initial. Now, how do we find final? In the final state, we are going to have that the wheel spins in the opposite direction, which means that you're going to have a negative angular velocity. Initially, we had a positive angular velocity. So then the person is also going to start rotating with omega final. So for the person, we have that they were approximated using 1/2 mass radius squared of a cylinder. And then for the wheel, we had 2 over 5 mr squared. So then L final is going to be the sum of those two times their respective speeds. So we have I of the person omega final plus I of the wheel times negative omega initial, and that's going to equal to 1/2 mass radius squared times omega final minus 2 over 5 mass radius squared times omega initial. So then you're going to set these two equal to each other. So here is now our equality. We can now move some terms. We can add 2 over 5 mr squared omega initial to both of our sides and add this here as well. So this is going to cancel out, and you're going to have 2 over 5 and 2 over 5. 2 over 5, that's going to be 4 over 5 mr squared omega initial, which is equal to 1/2 mass radius squared omega final. So then we see we have both mr squared on both sides. We can cancel that out, and we're left with 4 over 5 omega initial is equal to 1/2 omega final. So what we want to do is solve for omega final. What we'll do is we need to isolate it, and we're going to multiply both sides by 2. So then 2 times 4 is going to give you 8 over 5 omega initial. And here we have that canceled out. So omega final is equal to 8/5 of omega initial. And the reason why this makes sense is because flipping the wheel reverses the angular momentum. So the person must rotate on their platform faster to conserve the total angular momentum. Now, we're asked in part B, does the kinetic energy of the system change when they flip the wheel over? Well, is there a delta K? Well, initially, you had 1/2 I of the wheel times omega initial squared. That's 1/2 times 2/5 mass radius squared omega initial squared, which is equal to 1/5 mass radius squared omega initial squared. That 2 canceled out. And in the final, we have that both now are going to be rotating. So this is 1/2 times 1/2 mass radius squared times omega final squared. 2 times 2 is 1/4 mr squared omega final. So this is kf for the person. Now for the wheel, we're going to have kf is equal to 1/2 times 2/5 mass radius squared times omega initial squared. So kinetic energy is dependent on omega squared. So because it's squared, that means that direction doesn't matter because it's always going to be positive. This is equal to 1/5 mass radius squared omega initial squared. So now if we have our omega final, which is this expression, right, we can take this and you can actually substitute this in. So you're going to take omega final, and where we see our omega final in the relationship, we have kf here, right? So then we're going to have omega f squared. That's going to be 64/25 omega initial squared. So what we did was we basically just squared this whole thing. And when you do that, you're going to have that the kinetic energy of the person is going to be 1/4 mr squared times 64/25 omega initial squared, which is the same thing as 16/25 mass radius squared omega initial squared. So then your kf total is equal to 16/25 mr squared omega initial squared plus 1/5 mr squared omega initial squared. And we know that 1/5 is basically the same thing as, it is the same thing as 5/25. So that's 5/25 right there. Mass radius squared omega initial squared. And this is 16/25 mass radius squared omega initial squared. So this is equal to 21/25 mr squared omega initial squared. kf total. So this is kf total, right? 21/25 mr squared omega initial squared. And then k initial is going to be 1/5 mr squared omega initial squared, which we can rewrite as 5/25 mr squared omega initial squared. So if we compare these two, we can clearly see that kinetic energy final is greater than kinetic energy initial. Therefore, kinetic energy increased, and that means that the energy came from the person doing work, which converted internal energy into kinetic energy. So our angular momentum is conserved, but internal forces can add energy into the system.